Hi, grade 11. This is Ms. Canton. I'm going to try and talk louder this time. Hopefully you guys can hear me. What we're doing today is we're doing section 6.6. I want to talk a little bit about your schedule. So originally, you're supposed to have a test on Monday, but we are a day behind. So right now your test is going to be scheduled for Tuesday. I'll talk more about that on Friday. This is the last section we have to do. Friday, I'll give you the pretest. So you have Friday and Monday to do the pretest. Friday, the grade 12s as well have a work period. So you should be able to access some of my help then. If you're finding you need a lot of help, the times to come for help are before school, lunch, after school. I'm at the drama. I'm staying at the drama on Friday, so that'd be a really good time to find me as well. So those are times to access me. Okay. We're going to be working on section 6.6. I am following the textbook. So if you want to get Mrs. Van Dam to pause, you all can open to page 336. What we're doing now is we are doing the Explorer. So we have the following system of linear inequalities has been graphed below. So we have this system here. And one thing I noticed first of all of these are greater thans or less thans or greater thans or less thans or equal to's. They all have equals to. That's what I'm trying to say. My eraser works now. This is exciting. So you'll notice on my graph I have solid green lines and I've colored in green because is this discrete or continuous? Very good. It is continuous. Okay, so I've graphed this and I can see that my darkest part shaded in is this region right here. This is my feasible region. All of this shaded in, nice and green, is my feasible region. What the question has asked us to do is it says for each objective function, so here's one objective function they've given us, what points represent the minimum and maximum values? So we learned in 6.5 that it's the points, it's the vertices are the only ones that we have to test. So these vertices here. So let's try this equation. So first of all, they said, okay, this is the objective function. T equals 5x plus y. And let's sub in the first point, 0 and 4. So we're going to sub in 0, 4. I'm going to make a little table. You guys can either follow along with me in your notebook, or if you want to just watch, you can do that as well. Okay, so subbing in when x equals 0, we have 5 times 0 plus 4. Our answer is 4. Our next point, we've done this one. Let's try the numbers 3 and 4. We have 5 times 3 plus 4. That's 15 plus 4 is 19. Next point, let's do 0, 3. We have 5 times 0 plus 3 is 3. And our last point is 3, 2. We have 5 times 3 plus 2. 15 plus 2 is 17. So we can see we're looking for our minimum and maximum value. We have a maximum right here. So we have a maximum at the 0.34, and we have a minimum at the 0.03, a minimum. Okay? So we've done this one. Now it says, okay, but what if it was x plus 5y? T equals x plus 5y. Okay, let's set up another little table here. So let's first of all, let's do the 0.04 again. We have x, which is 0, plus 5 times 4. 5 times 4 is 20. Running low on space. Let's try the 0.34. I go 0, nope, x is 3. Plus 5 times 4. So 20 plus 3 is 23. Okay, we have 0, 3. So we have 0 plus 5 times 3 is 15. And finally, we have the 0.32. we have 3 plus 5 times 2. Well, this is 10 plus 3 is 13. So here we have a maximum at this point. Here's our maximum, and our minimum is at this point. There's our minimum. Interesting. Interesting. Maximums and minimums. Okay, so again, we're doing those vertices of the feasible region are what we test into our objective function to optimize whether we're looking for the maximum or minimum. So you guys are saying this is nothing new. In fact, this is what's new. So what we're going to do now, we're going to solve an optimization problem using linear programming. We're going to begin by creating algebraic and graphical models. So we're begin by creating linear inequalities. Then we're going to graph them. So creating them is the algebra part. Graphing them is the graphical. Then we're going to use some objective function. We're going to have to create an objective function to determine which vertex of the feasible region results in the optimal solution. Okay, here's the steps. First of all, we do algebraic. We do a defining statement, a let statement. Then we do the restrictions. Okay, so are we only talking about things that are less than or equal to 4? We are doing linear inequalities that describe these constraints. And finally, we create an objective function. Usually we're talking about cost, or we're talking about profit. Some sort of equation that we're trying to optimize. Then we graph it to find the coordinates of the feasible region. So we're trying to find a triangle or some sort of quadrilateral. We're trying to find some region. We evaluate the function, so that function we made up here, we evaluate it by substituting the values into each vertex. We compare the results and choose the solution. So that's kind of what we did here. We compared all these results. We said 4, 19, 3, 7. Well, what's the minimum? What's the maximum? We compare those. And here's the new thing we're doing. We're verifying that the solution satisfies the constraints of the problem situation. So if my answer, if I was looking for a maximum of this first optimal function, I've done all of my work I had to do. It's been graphed. I have my linear inequalities, my constraints. The last step I'd have to do is I'd have to confirm that the point 3, 4 satisfies each of these. That's my final step. So let's see if 3, 4 satisfies this. So my point 3, 4, this is my x value, that's my y. Is my y greater than or equal to 0? Is 4 greater than or equal to 0? Yep. X is greater than or equal to 0. Is 3 greater than or equal to 0? Yep. Is y less than or equal to 4? Is 4 less than or equal to 4? Yep. X less than or equal to 3? Is 3 less than or equal to 3? Yep. Okay, here comes a tough one. 3y greater than or equal to negative x plus 9. So 3 times 4 is 12 greater than or equal to negative x. Negative 3 plus 9 is 12 greater than or equal to 6. Bingo. Okay? That's the only new step we're adding, is that we have to verify. And I know what you guys are saying. Why do I have to verify? Because this is one of those tests that you can hand in and you can know with confidence that you have 100% because you verified it all. And you know what? If you verify and you don't get the right answer, then you're going to go back and you're going to fix it up. Oh, look, I said negative 3 plus 2 was 5. That's not right. Fix it up, 100%, wham, bam. Okay? So I'm just going to read through a sample that you have in your textbook. This is on page 338. We're going to go through this one together. So we have LNG Construction competing for a contract to build a fence. The fence will be no longer than 50 yards and will consist of a narrow boards that are 6 inches wide and wide boards that are 8 inches wide. There must be no fewer than 100 wide boards and no more than 80 narrow boards. The narrow boards cost $356. The wide boards cost $436. Determine the maximum and minimum costs for the lumber to build the fence. There's tons of math language here. No longer than, um, no fewer than, no more than. And then we have maximum and minimum tells us we're doing optimization. So let's see how they went through this. I think, what did we say again that our first step was going to be? Let's see if they did that first step. We said create an algebraic model. So they're going to do some let statements and they're going to have some inequalities. Ooh, let N represent the number of narrow boards, let W represent the number of wide boards, and let C represent the total cost. So C is what we're going to be optimizing. The restrictions, N must be a whole number and W must be a whole number. So they're saying they cannot use half boards. Okay? Since they represent the number of boards needed, they must be whole numbers. So they must be going to some sort of hardware store that doesn't cut boards in half. Okay? There's no fewer than 100 wide boards. W has to be greater than or equal to 100. There's no more than 80. N is less than or equal to 80. The fence is no longer than 50 yards. So and is made of 6-inch narrows. So there's 6 inches times each narrow and 8 inches times each wide. No longer than, which means less than or equal to, 50 yards. So they did 50 times 36. Where did this 36 come from? I converted yards to inches using the rate. 36 inches is 1 yard, since the coefficients of the other terms are in inches. Okay? So some of you might have thought you just needed to do 50, but then you're comparing apples and oranges. Inches to yards. It had to be in the same units. Okay? A couple more constraints that they had here. They said N had to be greater than or equal to 0. Can't have negative boards. W has to be greater than or equal to 0. Can't have negative boards again. And these were all the ones that we just did. These ones we just did up above there. Okay. The optimization function was, or the objective, sorry, function. Each narrow board cost $3.56. Each wide board cost $4.36. If you add them together, were we trying to minimize or maximize this cost? We are trying to, we want to find the minimum and maximum. We want to know both. Okay. So what they did is they graphed these. You'll notice that they have stipple and they have orange. Why is it orange stippled? Okay. They said that's going to be because it's discrete. We're only talking about whole numbers. And Brandon, you're going to say, but really, to be correct, we should have a bunch of dots here. And you're totally right. But they simplified. Okay, so they graphed it and they found this feasible region right here. Okay, from that feasible region, they got their 4 coordinates of their boundaries or their vertices. Okay, so now what they're going to do is they're going to sub each of these in to the optimal function. No, I keep calling this objective function. I always want to say optimal. They put it into the objective function. So first of all, they took this vertice right here, the 0 and 100, plugged it in, and they found out it cost them $436. Next, they plugged in 0 and 225. They plugged in this one. They found it was 981. Plugged in the next guy. Oh, no, that's here. 1,720. So what's their maximum and minimum? Here's your biggest cost. Here's your littlest cost. Okay, and they had a couple conjectures. They said that this top one right here is going to be the maximum, they conjectured, and this one was going to be the littlest, because they said since it's the farthest from both axes, which means it has the largest coordinate values, it means that we're going to put in the biggest numbers here and here. And they said, well, this one they thought would be the smallest because we're going to put a 0 in right there. Okay, that was their conjecture. Their conjecture was correct. Good conjecturing. Okay. So they said here is the minimum, here is the maximum. So normally that's where we stop. But the new thing we're doing today is we're verifying. So they're taking that point 0 and 100, that minimum, and they're checking it in every single um, constraint and showing that it's true. Okay? So this is the new step, showing that it's true. Okay? So you guys have some questions to do. I believe it starts with question 2 on page 342. The good thing about question 2 is that there's none of this decoding. You don't actually have to read it and it says no fewer than, no more than. They actually give you the constraints. So it's like in question 2, they've already done step 1, your algebraic model is done, and you just need to start here with graphing. So what are you going to need? Graph paper. You're going to need some colored pencils, and you're going to have to get to work. So don't be afraid to ask one another quietly for help. If you come to a question you absolutely can't get, a partner can't help you out, Mrs. Van Dam can't help you out, put a Starby on it, move to the next one, and come for help. If you want my undivided attention, you need to come lunch, after school, before school. And if you need just a little bit of help, then you can wait for in class. But do know I have 2 classes going on. Okay, good luck.